Right. Yes, my background is drilling fluids. I've been involved in it for over 25 years. And I started up my own company, Downhole Fluid Solutions, in 2004. And I came across a problem, this problem first, that this material addresses in 2002. I'd never heard of it before. It was called wellbore strengthening. And one of the UK companies told me about it, and they needed an answer to this problem. Once I found out a bit more about it, I started working on it a little after I started my own company in 2004. And by 2008, I'd fully developed the product into a useful item, managed to get it patented, and then started talking to oil companies again, and all during this time I was keeping in touch with them to make sure I wasn't going down a dead end. And yes, they still wanted some physical material to overcome this problem in mature fields where the pressure had become depleted, but they still have to drill all these infill wells, and drilling these structures had become more difficult because they become differentiated. And you've still got the high pressure zones, but now by this time you've got a lot of low pressure zones through which you find induced fractures are created and drilling fluids lost. So I was told, we want something to strengthen the near wellbore, a physical material. Other people were talking about it's just lost circulation, but the two are combined, really. And the main problem is losing so much fluid. And you don't have control of your well in these mature field reservoirs. So could I come up with something that would control the lost circulation and hopefully increase the near wellbore strength? So I came up with this idea, and I've been using it, knocking around in my head since 2002. And I looked at it, and I've been used to working with all sorts of different materials, having worked in the lab as well as in the field by this time. And of course they want everything. It's got to be green, that's the first thing. It's got to be non-hazardous. That should be top of the list really these days. But their recourse at that time was, if we can't, we're in the reservoir and it's really uncontrollable and we don't want to put LCM materials down there, we have to cement it. Well, cement in the reservoir is not a good idea, as everybody knows, and they had to meet all these parameters. And this I did. It took me about 2 years once I really got into it, and come up with a material that looked useful. So eventually, I managed to find, the trick was to find something that would bond this material together. So it's made up as a liquid in water. You can hand around and have a look. And the final product is one of these. I'll hand that around. So what I'm doing is making a fluid with a high solids content that can be bumped down through the drill string, so you don't have to pull out of the hole. And you can pump this into the zone where you have got your induced fracture, and it acts like cement. And it must never, one of the big things is it must never set up flash set in the string. And it must be easy to use, no problems related with it, over a wide range of temperature. So I've done this, and it has two other very important properties that were additional to anybody's first requests. In situ, it will remain slightly malleable, so it will deform as you continue drilling. So it will always maintain contact with the rock, so you'll seal it. The seal is maintained. And also, this was the final one, after I'd been seeing a few people. Nobody mentioned that it had to be fully, partially removable, yes, but fully removable. And this product, once it's in place, will allow you to stop your losses, increase the wellbore strength, and then once you've reached TD and produced the well, whether it be cased hole or open hole, it will be removed, remembering the fact that produced fluids are a mixture of oil and water. So the components are a mixture of organic and inorganic material that is soluble completely in those produced fluids. And it'll depend on the temperature and what particular properties that mixture has to give you a time idea of how long it's going to take to clear it. But you don't have to use any intervention, because another remedy might employ, say, the use of carbonate particles to seal it, which is currently being done, which can be removed by using acid when you're in a sandstone, say, or sand. But if you're in a carbonate reservoir, then you don't really want to use acid. So this overcomes that problem. So it's a mixture of a synthetic organic compound and an inorganic compound, and it's a dry product, so it's easy to use. And this is mixed in water. You put in an activator, a liquid activator, and the only polymer in it is xanthan gum. So you've got a mixture that looks like a drilling fluid, and has some properties like it, but it has no fluid loss properties in its liquid state or its initial state. So that when this is just a standard mixture. So you've got about 200 pounds per barrel of the solid material in powder form, in suspension. So very simple. You mix it as you would in any drilling fluid, in any tank. So there's no problem at all. It's non-hazardous. It's very easy to mix. You can add it as fast as you like, and then leave it. And you can leave it there for as long as you like. And I've actually mixed this material and left it for a couple of years and then used it. It actually improves. It's easier, and you get a better aggregation and compaction when it's actually put in place. And what you're seeing there, that little disc, is a composite of the solids which have been dewatered, and then the material then, so you displace the fluid to the induced loss zone, and this is just a rough idea of how you should do it, but each well will be slightly different. And once it's in place, you've got a volume over the section, bearing in mind that about 50 barrels will contain 16.5 barrels of solids, which should be enough to seal off and bond to a substantial amount of the formation. So you displace it slowly and rise to the pressure at which you lost the fluid, and then gradually increase that, watching everything that's indicated on the drill floor, and displace, say, 90% of the whole fluid, leaving some in the wellbore. And you stop pumping and allow the material to go into the fracture, and the solids become dewatered, and then they aggregate, and then with the activator that's in it, it activates the organic material, which fuses it together. So you end up with something that's, the best analogy is something like tarmac. So you've got inorganic solids and an organic material that will, most of the time, for our purposes, tarmac will remain a solid. If it gets hot, it's slightly, you know what it's like. So the same thing applies to this. So it has a use in being malleable, in that that will cause the ROCKWELD to remain bonded to the surface of the loss zone, whatever that may be, and it will change shape too. And that means you can prevent more loss of fluid either way, or flow of fluid either way, including gas. And this has been tested by, I've used this and tested it with 4 big companies. But the main thing is getting a well to try it on. That's the big stumbling block. So you carry out your pressure test on the rig floor, and any ROCKWELD fluid, as is in the little pot there, will remain fluid, because it's not a chemical reaction that's going on here. You're making use of the physical properties of those 2 main ingredients. The inorganic portion, which could be anything, it could be ground granite or it could be limestone, but in this case it's salt, hence the water solubility portion element. But the fluid itself will remain safe, and it's been tested by Total and left it for 24 hours at high temperature, applied 15,000 psi to it, and next day pull it apart and it remains fluid because there is no chemical reaction. And that's the big thing that drillers are scared of, putting anything down their well like this, is that, is this going to lock up on me in the drill string so that I have a big problem? No, it won't. You'll just flow it out. This just gives you an idea of how it's tested. The black, the black portion there is the ROCKWELD, and beneath it is a sand bed, which just represents the formation. And it's been compacted in the cell, and then on the right-hand side is a cell that has water and oil separately, and backflowed through it to show to prove its removability. And it's not a true return permeability test. What you're trying to prove here is just its total removability. And that just gives you an overview of what it should look like down a well, what you're trying to overcome. It also has, I've picked up various suggestions from various people along the way that can it be used for this, can it be used for that? It could be used. I haven't used, this has not been used yet. It's been, as I said, it's been tested by 4 major oil companies. But the big stumbling block is giving a well, a test well. And essentially that's where I am at the moment. And we could have any one of these situations to test it on. And now I'm hoping, I've got some interest in the Middle East, which is quite surprising, from the Chinese. And hopefully they might even be the first ones to use it. But at the moment, I'm stuck there waiting for that well. Thank you very much. Any questions?
Thank you, Angus. So, thank you very much. Let me ask you a question. Who do you actually see as your main target customers then? Is it big oil companies? Is it drilling companies?
No, oil companies. Definitely oil companies. I've talked to many oil companies and operators all, not won't say all around the world, but Europe, Africa and the Middle East. And when I've been asked the question, when I asked the question of them, what is the problem that you've got and what's the problem that you see? It's in these depleted fields where they have this problem and they need something to overcome it when the time comes. And at the moment they don't have an answer. But then I asked, well, where is this? And they said everywhere. So can you put a figure to it? No. It's just big. So I think once we can get it moving, for instance, in India, in Mumbai High, which is a heavily fractured carbonate reservoir, and they've had problems there of lost circulation, various types from A to Z. But this has been addressed at one particular zone that they have tested for, and I have tested it with them and got their approval. But it always comes down to, okay, passed it, your guys have said okay, they approve it, and better than anything else that's been suggested, where's the well? And then they stop. They want to be second.
Most of the industry wants to be second.
So who wants to be first?
Okay. Okay, thanks for answering that. Anybody got any questions? Yeah, a couple.
Just, I mean, as you say, lost circulation is a massive issue. It's just interesting how you describe that it's so it can be dissolved by, once you create this sort of layer, it can be then dissolved by the oil and the water. Production, yes. So, do you think that it's dissolving, or do you think you can just sort of, it creates a sort of a skin that you then just sort of pop off?
It'll depend on the particular problem there. But with an induced fracture, I see this as being squeezed into the induced fracture, which can be any sort of size visually. And then it'll set there, fuse, aggregate, compact, and squeeze together. And then once it becomes that aggregated, fused form, it will stay in contact with the formation, seal it. But then you can continue with your drilling to TD. And you may have to repeat this. And then once you get onto production, once you've got flow initiated over the surface of the crack, if you like, that will increase once the flow is started, the flow rate will increase and the removability will increase. But there isn't one piece of kit in the world that I've found that's exactly useful to test that. In Total were building one 2 years ago and I was going to use it, but it cost them over $1 million, and I was there the day that they said, right, it's finished, and then somebody said, no, it's not. And they made a slight error in measurements and they had to scrap the whole lot. So I never got to test that.
Okay. So it does need some flow, because otherwise,
yes.
Otherwise the water or oil-based mud would just dissolve it.
No, it doesn't. No, oil-based mud will not. In theory, yes, oil-based mud would tend to, in time, dissolve that. But again, only if you've got flow. You can have oil-based mud and this material face-to-face in the cell, and I've done that. And you'll get a little bit of the surface will get sticky, but it won't dissolve. It just it comes to a state of equilibrium. And until you get flow, that's the only change. You'll get a bit of change there at the surface, but it'll stay inert and in equilibrium until you change the pressure and flow it either way. If you float it from the top down, you have to induce a fracture again. But to flow the well is the best way to remove it, assuming you've done your homework and you know the properties of the oil and water are.
Okay, we have. Yeah, you've got a microphone? Yeah, please.
Adrian Hefford from IHS. Hewitt field is very low pressure and might be used for carbon storage. How would your plugs work in a carbon dioxide environment?
In that situation, well, I haven't thought of that one. I don't think that would be a good application for that, for this material, for that purpose.
Yeah, please.
Every time you talk about cleansing the material out, you talk about oil, water. Do I understand that the presence of water is needed there for some chemical reason?
Not for a chemical reason, only for if you wish 100% removability. Now, whether you need 100% removability is another point. I mean, I started off working with this with a mixture of an oil-soluble material and an inert material, which was limestone. So in that case, I could get 50% removability by the produced oil affecting the organic material, and it's totally soluble. So you then release the solids, which would flow to the surface, which is a relatively small amount. And that might be entirely sufficient to give you the result you want. But I was given this instruction, look, we want 100% potential removability, can you do it? And this was in India. So I went back and thought again, yeah, we'll change the inert material to salt, which I'd had a lot of experience with, and I knew the removability aspect was a feature of LCM pills in reservoirs, which I'd used for years and I still do. So by combining the two, we could get a product that was potentially 100% removable from the produced fluids in depleted fields.
Then in most initial fields where you have only oil being produced, you have a problem.
Then yes, but this is addressing mature fields, as I said in the beginning. This is for mature fields where you've got a lot of oil, the vast production's gone, yeah, but you've still got a lot of oil that you want out. How do you do it?
Thank you.
Could I just ask, is there salt in solution? So is it a brine? Actually?
It will be mixed, in that case, yes, it's mixed in brine, yes.
Okay, so to answer the question about carbon dioxide, if you introduce supercritical carbon dioxide, it would actually precipitate the salt from solution, and the carbon dioxide would go into the solution.
I'm using this material as you're drilling the well.
Yeah.
Your carbon dioxide is going to come from where?
No, there was an earlier question about carbon dioxide sequestration.
Yes, yeah, you're talking about CO2 storage. Now, if you're drilling a well for CO2 storage, I don't know whether the use of this material makes sense.
I'm saying it doesn't.
No, I'm saying it doesn't.
We have one more question.
Yeah. If you were drilling a well and you were about to enter what you thought would be a total loss circulation zone, could you use it as a sealant during the actual penetration process, or wouldn't there be enough pressure to activate the sealant?
It depends what you mean by total loss. If you're talking cavernous situation, no, this is not for that. As it said there, when you're drilling through a structure where it's reasonably intact, but you've got weak zones where you get gives rise to induced fractures. That's where it's useful. For that situation, and dealing with what you're talking about in the Middle East right now, that's a different situation for a different material, and maybe not even something of a chemical nature.
I'm thinking about kind of Kurdistan wells, that kind of thing.
Well, I've been to Kazakhstan, and I wouldn't even entertain the idea of it where they've lost, what was it, 10,000 foot of drill string and couldn't even tag it. I mean, it's like drilling into the Grand Canyon, and you're never going to fill that with anything.
I agree with that. Okay, anybody else? Okay, well, thanks, Angus, and thanks especially for agreeing to step in. Thank you.